So let's take a look and again, just kind of remind ourselves how we do this. So this is a basic stoichiometry problem as we talked about last time. And remember, kind of really the whole purpose of stoichiometry is it's really just a conversion factor or really conversion. And that's because you're usually given information about one thing in the reaction, but you're kind of interested in somebody else in there. So you need a way to kind of convert from one to the other. And in this particular case, we are starting with 81.75 grams of lithium. Ultimately, we want to know basically how many grams of hydrogen there is. So that is really where the stoichiometry part is going to come into play. It's going to allow us to go from lithium to hydrogen. And again, we're going to use the equation as a conversion factor. Now, the first step here is already done because we did the first part of this problem, I think, last time. So we do have a balanced equation. Remember that none of this works if the equation is not balanced. So that's always the first thing that you want to make sure that you have when you're doing this type of problem. So step number 2 here, we do need to do, they gave us here our information in grams. So step number 2, we're going to convert to grams, convert to moles. We will need the molar mass to do that. In this case, we can just go to the periodic table and grab what we need there as our conversion factor. So taking our 81.75 grams of lithium, again, using the molar mass from the periodic table as a conversion factor, we're going to put grams on the bottom so they cancel. Grams of lithium will cancel. Again, as we talked about last time, you don't necessarily need to get an answer at this point. You could do it all in one calculation, but if you did get an answer, I would not probably round too much at this point. So I'd take it to a few extra digits and not drop your calculator just to make sure you're all good here. So we'll go there to lithium. Now that we have that, we need basically the third step, which is the mole to mole relationship. That again is the stoichiometry part. So we want to look at the balanced equation and we want to find the two things we're interested in. And obviously in this case, it is the thing that was given to us, which is lithium, and also what we're trying to find, which is H2. And from that, we could get the mole to mole relationship. And remember, it's just the coefficient. So nothing tricky there. It's just from the balanced equation, the coefficients. That is why it's important to make sure that you do have a balanced equation. Otherwise, you will get the wrong relationship in most cases. So in this case, we could see from the equation that we get 2 moles of lithium for every 1 mole of hydrogen. Remember that that will give you pretty much 2 conversion factors that you could use. You're only going to use one, whichever one you need for your particular calculation. And in this particular case, we're going to continue on with our number from above. So that's 11.7778 moles of lithium. We want to go opposite to cancel. So conversion factor here on the right is what we want to use. And again, that comes from the equation. 1 mole of H2 and 2 moles of lithium. The moles of lithium are going to cancel. And that really is the big stoichiometry move right there, just using a conversion factor. Again, if you do get an answer here, don't round too much probably at this point, and that will take care of step number 3. Any questions on up there? In this particular case, we're actually looking for grams, so we do need to do step number 4. We do need to remember, though, that we are now at H2, so we do need to get the molar mass for H2 so that we could use that as a conversion factor. So that would be 2 times 1.008 grams per mole. Gives us 2.016 grams per mole as our molar mass. Remember as well, when you do the molar mass, it is just for the formula by itself, no coefficients or anything like that. So just the formula to the periodic table. So 4th step here, taking our number here and continuing on. In this case, we do want grams up on top so that we end up with grams. Moles of H2 will cancel, and that's going to get us there about 11. At this point, you can kind of round it to some proper digits here, 11.87 grams of H2. So what that number means is if we did this reaction, we put in there 81.75 grams of lithium, everything went perfect, no side reactions, nothing was lost. You should produce 11.87 grams of H2. This is also known as the theoretical yield, how much you would produce. Any questions on any of those steps? Once again, as I mentioned, you can go from step to step, which is truly how they want you to do it here. But I don't care if you break it up in each step, but you can't go obviously from one step to the next without getting answers in between. Yeah. Any questions on that one there? So as I might have mentioned last time, pretty much basic stoichiometry problems are like this, where you're just given one piece of information about somebody in the equation. You're looking to find out something about somebody else in the equation. You should always follow those 4 steps. All right, so let's take a look at another one here. All right, so why don't you give this one a go. If we took 765 grams of C6H12O6, we want to know how many grams. That's a highlighter. That's not going to work. We're looking for how many grams there of CO2 would we produce. So carbon is 12.01, hydrogen 1.008, and oxygen still 16. All right, bless you. Give it a go, see what you come up with. These 4 steps, we are given really information about this guy, but we're interested in the CO2. So it is a stoichiometry problem. We have an equation. I see some coefficients, so I'm going to assume that it's balanced, and it is. Next thing we need to do is we do need to do step number 2, which is take whatever they gave us basically and convert them into moles. To do that, though, we will need the molar mass from the periodic table to do so. So that's going to be 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogens, and 6 times 16 there for all the oxygens. That looks like 180.2 grams per mole. That's going to be our really conversion factor to go from grams to moles here. So we'll take our 765 grams. Again, using that from the periodic table as a conversion factor here, we do want grams on the bottom, 180.2 grams per mole here, C6H12O6. The grams are going to cancel. And once again, if you did get an answer here, probably not too much rounding at this point. 4.2528, we'll call it, moles of C6H2O6. That takes care of step number 2. Step number 3 now is going to be our stoichiometry part. And again, we're going to go to the equation and look at the 2 things we're interested in. That's one of them. And obviously what we're trying to find is another. So we can see from the balanced equation that for every 1 mole of our C6H12O6, we will produce, in this case, 6 moles of CO2. Once again, that is just the coefficients. And we will use that as a conversion factor. So continuing on here with my number from above. In this case, we do want the moles of C6H12O6 to cancel. So we're going to put that on the bottom so that they do cancel. And up on top will go our 6 moles of CO2. That is the stoichiometry part. That's what's going to allow us to convert from the C6H12O6 into the CO2 in this case. And we're going to basically times it by 6. Once again here, I'm not going to round too much here since this is not really my final answer. That's CO2. So that is step number 3. Lastly here, we want grams, so we will again have to go back to the periodic table though, and calculate the molar mass here of CO2. So that's going to be 1201 for our carbon, plus basically 2 times 16 for our oxygens. That's going to give us a 4401 as the molar mass from the periodic table. Using that here with our number from above, 25.471698. I really did not round on that. Let's CO2. And we're going to use our grams up on top in this case so that we do end up with grams. The moles of the CO2 will cancel. And that's going to end up with about 1,120 grams of CO2 would be produced in this case. Again, this would be our theoretical yield as it's a product. Remember that a yield is a product. And again, this would be based on what we would be looking for. You do get something like 1,121 on your calculator there, going with 3 significant figures off of that number, which is really the only number in the problem. So that is why we rounded there to 1120. Once again, you could roll one big calculation all the way through that way, if you like. Any questions on that there? All right, one more just to make sure here. Scroll this across just in case. All right, give that one a go there. How many grams of cisplatin, whose molar mass is 300.1 grams per mole, can be obtained by starting with 0.7752 of K2 PtCl4, molar mass from the periodic table, 415.1. So they were nice enough to give you the molar mass without you having to go to periodic table. So see what you... Okay, so let's take a look. So again, we're going to follow these steps here. We're going to balance the equation, which it already is. We're going to convert to moles. So they were nice enough to give us the molar mass. If they did not do that, obviously you would need to go to the periodic table and calculate it yourself. So since they did, I'm going to use it here. And for step number 2, basically here, we got 300, I think. It is 415. I'll try that one. So we're going to go with 415.1 grams per mole here. And again, you would need to calculate that yourself if they didn't do that. If I stop right at this point, I have now converted into moles of my K2P2Cl4. That would be the second step. I'm going to do it all in one calculation again, just to show you here what it would look like. At this point, I can move to the third step, which is the mole-to-mole relationship, which from the equation, we can see that for every 1 mole of this guy, we get 1 mole of our product there. So again, we're going to continue on. Remember, opposites cancel. So from the equation here, 1 mole of K2PtCl4, 1 mole of our product. Too long of a formula to fit. There we go. We'll make our parentheses bigger, I guess. There we go. And again, at this point, if we were to stop, the moles of our K2PtCl4 would cancel, and that would be our third step. Our last step here is, again, we are looking for grams, so we will do step number 4. Once again, they were nice enough to give us the molar mass. Otherwise, you would need to go to the periodic table there and calculate it yourself. And we want grams up on top so that we end up with grams. So of our product here. And that's going to get us there, looks like 0.7752, basically times 300.1 divided by a 415.1. Looks like 0.5604 grams of PtNH3Cl2. Again, this is because this is a product, this would be your theoretical yield in this case. Again, you can hopefully see a pattern here. It is basically 4 steps. 1, 2, convert to moles, mole-to-mole relationship, and moles to some other unit. Any questions on that one there? So what we've been looking at are really what I call basic stoichiometry problems. And again, really what a basic stoichiometry problem is you're given, as we've seen in these examples, basically one thing, either on the right-hand side or left-hand side of the equation, and you're trying to find something else in the equation. So those, you always follow the 4 steps. Again, if something's done for you, just go ahead, don't go backwards. Also, a reminder that you can do stoichiometry calculations on the same side of the equation like we talked about previously. You do not have to cross over the arrow. You obviously can cross over the arrow and do relationships on opposite sides, but you could also do the same calculations without necessarily going, from one side of the reaction to the other. So you do it between two reactants, two products, or reactants and products. You could start with products and go to reactants. It doesn't really matter which direction you start at. Any questions on that there? All right, then let's talk about the next important part of stoichiometry, which are limiting reagents. They're also sometimes called limiting reactants. And whenever we do a reaction, there's always a reactant that pretty much gets used up first. So when we do a reaction, there's usually a limiting reagent, and again, sometimes referred to as a limiting reactant. And when you do that reaction, there's always at least one that will be used up first before the other one. And that's really important. For example, if we had a very simple idea here of A plus B makes A and B, and if A was my limiting reagent, the problem is as soon as I run out of A, would I be able to make any more product at that point? I would not, right? Because I'm missing kind of a key component there. So when we run out of our limiting reagent, there's no chance that you're going to be able to make any more product. So the limiting reagent is always the most important because it will determine how much product you will produce. The other reagent, for example, here B in my example, is known as the excess reagent. And the excess reagent, much like the name implies, you have plenty of. So you got plenty of that one. You dumped a bunch of it in there. It's not a problem. You actually will have some excess reagent still left over when the reaction is done. All the limiting reagent will be gone, but you'll still have some of that excess one. So for example, the other day when we did that experiment, you weighed out a certain amount of grams of the solid and you mix it with a bunch of liquid. The liquid part of that was your excess reagent. The grams that you weighed out, which is a smaller amount, it was actually your limiting reagent in that particular case. So as I mentioned before, the excess reagent is the one that you have plenty of. So the good news is, for the most part, these type of problems are done the same way as basic stoichiometry problems. You still really balance your equation. You still want to convert to moles. You still at some point want to use your mole to mole relationship. And you want to go moles to some other unit. The difference is, and there's a couple of different ways you can actually do these type of problems, but the way we're going to be learning it in here is right around here. You need to determine your limiting reagents. We'll talk about how you do that in just a second. And once you do that, you should use always your limiting reagent for the rest of the steps. Yeah, so the rest of the steps, you need to use your limiting reagent. So we basically are just going to kind of follow the same steps that we did for basic problems. We're just going to kind of insert a little calculation in the middle there to figure out which one's the limiting reagent. And at that point, you can just kind of continue on with your calculation. So here we go. We got like workout buddies here. We want to make a guy and a girl workout buddies. Obviously, we could see for a complete set, we used up 3 of them. And obviously that would mean here that the guys is our limiting reagent. We actually have excess amount of the women workout people. We could also figure out as well, which is a common question, how much of the excess reagent is left over at the end of the reaction. In this example, we would have two unpaired people, and that would be how much we have left over. So those are very common sort of questions in these type of problems. You're oftentimes asked, how much product will you produce and how much of that sort of excess reagent will you still have over? How do you know, for example, it is a limiting reagent type problem? Here's how you know that you have to do that extra step. The way that you know it's a limiting reagent problem is you can convert to moles of each reactant. So basically, if you're given a problem where you have information about, say, both reactants, and you have enough information about both reactants that you can easily just simply convert those numbers into moles, then you know for sure it is a limiting reagent problem. If you think about the examples that we did previous to this, we pretty much had one piece of information, only about one reactant, not really both reactants. So if you're given that information about both reactants in a lot of cases, that's usually a really big hint that you're doing some type of limiting reagent problem. So let's just say that we took this equation here, and we'll just do a little example that we're going to start with 4 moles of S and 20 moles, 4 moles of S and 20 moles of F2. And we want to know, for example, how much product we would make here. So we want to know how much product here. All right, so first off, we're still going to follow our basic steps, which is we're going to get a balanced equation, which we have obviously here. We want to convert to moles, which we actually don't need to do because I already have them in moles here. That's not in moles, that's actually moles of sulfur. Huh? There we go. So we already are in moles of each of these guys, so that is actually done for us as well. So what I do see, though, is I definitely have moles of S and I have moles of F2. That is the part that tells me this is a limiting reagent problem, right? Oftentimes you may have grams of both of those guys, which obviously you could convert to moles. So as long as you could get whatever they give you into moles of both reactants, this tells me it's a limiting reagent problem, which means that's the part where we're at, where we need to do a calculation to figure out which one's the limiting reagent. So to do this calculation, you could choose either reactant once it's in moles. And what you're going to basically do is just a little calculation to determine if I want to use up all of one of the reactants, how much of the other one do I need? So for example here, to determine which one's the limiting reagent, I want to know if I want to use up all my iron or my fluorine, how much sulfur is needed. And we can think of these original numbers as our starting amounts of each of these, right? We got 4 moles of sulfur and 20 moles of, I keep wanting to say iron, fluorine in there. So here's what I'm going to do. I want to take up the starting amount of fluorine, which is 20 moles, and I'm going to do just a basic mole-to-mole relationship between the two reactants. So from the equation, it's 1 mole of sulfur gives me 3 moles of fluorine. So we're going to use that. So 3 moles of fluorine gives me 1 mole of sulfur. So that's just from the equation, just a simple little calculation here. I'm basically going to divide by 320. This means 6.67 moles of sulfur is needed. First off, any question on the calculation? So just really a calculation between the two reactants, very short little calculation. And what we're going to do with that number is we basically want to see, do we have enough of it? So what this basically tells me is I need, if I want to use up the other reactant, I need 6.67 moles of sulfur. How many moles did I start with? Started with 4 moles, all right? So I want to compare how much is needed to what I started with. And in this case, if I need 6.67 moles of sulfur, but I only started with 4, I do not have enough. And because of that means that this guy here would be my limiting reagent, the sulfur. The good news is if you can identify sulfur as your limiting reagent, by default, in this case, the fluorine would be my excess reagent. So as long as you can identify one of them as either being limiting or excess, the other is happening to the other. First off, any questions on that calculation? Now, does it matter which one you choose? It doesn't. So just to show you here, if you decided I wanted to do it, the other sort of calculation would be I want to use up all my sulfur. How much fluorine is needed? You would do a similar calculation. You would start with your sulfur, which is 4 moles of sulfur that you started with. You would use your same mole to mole relationship from the equation, which in this case we would flip it around. We would go 1 mole of sulfur on the bottom, 3 moles of fluorine up on top. The moles of sulfur will cancel. That will give me 12 moles of fluorine is needed. Now, in this case, when I look at fluorine and I compare it to how much I started with 20, I need 12. Do I have enough in this case? I do, right? I only need 12, but I am starting with 20. So I have enough. And if you do this calculation, you have enough, that means that this guy is actually your excess reagent. So you do not actually have to do both calculations in a lot of cases. You could just do one. You can choose whichever one you want to do. They both will tell you the same thing, which one's the excess and which one's the limiting. So again, if you figure out which one's the excess, the other guy's got to be the limiting. If you figure out which one's the limiting, the other one has to be the excess. Any questions on that there? So what is this helpful for? Well, once I figure out that in this case the sulfur is the limiting reagent and my fluorine is the excess reagent, I actually now could just pick up with my normal stoichiometry step, which is now we're going to actually do the mole to mole relationship. We do want to use the limiting reagent, and we do want to use the starting amount of the limiting reagent. So that would mean that we can now go to step 3 with our limiting reagent and go 4 moles of sulfur. We can now do it to our product. 1 mole of sulfur is 1 mole of SF6, and that would get us something like 4 moles of SF6. This would be our theoretical yield in, for example, our theoretical yield in moles. We could also do the 4th step here, use the molar mass of SF6 and convert it into grams if we want to know how many grams. So we could definitely go and do our 4th step moles to grams. Any questions on that there? Now, the other common sort of thing that you're asked, so I won't do the 4th step here, but I'll just do the other sort of common calculation that you do, which is we could actually use this calculation here for our excess reagent to figure out how much of our excess reagent would be left over. So if we wanted to know leftover excess reagent, you would take the moles that you started with of our excess reagent, which was 20. You would subtract it by the 12 moles that are needed. And that would tell you you had something like 8 moles of F2 left over, which again, you can use the molar mass of F2 to figure out how many grams that would be as well. So these are all sort of the questions that you're sometimes asked. How much product you would be produced should always be calculated based off the limiting reagent. Also, how much of your excess reagent is left over. Now, with that being said, if you chose this calculation here to figure out your limiting reagent and you were asked that question of how much of your excess is left over, you would need to go back and sort of do that calculation to figure that out, obviously, if you needed to. So this is the way that you can figure out the limiting reagents. You just take that short little calculation in the middle, figure out which one's the limiting reagent, and do it. The other more common way nowadays that people are taught how to do limiting reagent problems is they just do two separate calculations, one with, say, the first reactant to the product and one with the second reactant to the product. Just do the whole calculation. And whichever one produces the smallest amount of product would be your limiting reagent and your theoretical yield. So if you like that approach where you just do two separate calculations, you could do that. And again, that's a very common way these days that people are taught sort of how to do that. So what I mean by that is you would take the 4 moles, convert, obviously go mole to mole relationship to your product, do the 20 moles mole to mole relationship to your product, and whichever one makes the smallest is your limiting reagent and your theoretical yield. Any questions on any of those steps there? So let's take a look at one here together, I think. All right, so let's say that we had this reaction here, and we want to know, we're going to let 6.83 grams of iron react with 9.34 grams of sulfur. And we'll grab some periodic table information, iron 5585 and sulfur a little 3207. All right, so first off, even if they didn't ask you which one's the limiting reagent, which very commonly they do not ask you that, I know that I have 6.83 grams of iron and 9.34 grams of sulfur. I know I could get to moles of each of those things, and both of those are reactants. So because I'm given enough information about both reactants that I can get the moles, I know that this is a limiting reagent type problem. So I know I'm going to have to figure out the limiting reagent here. We're still going to roll through our normal sort of steps, no matter what sort of process you take. You need to start with a balanced equation, which it is here, so we're good. We need to convert to moles. In this case, we do need to do that, so that is what we're going to do. We're going to convert each of these into moles. So we're going to take our 6.83 grams of iron. We're going to go to the periodic table, use the molar mass of iron, 5585 grams per mole. And that is going to give me 6.83 divided by 5585, 0.1223 moles of iron. We're going to do exact same calculation for sulfur here, 9.34 grams of sulfur. Going to the periodic table here and grabbing the molar mass. We're going to put the grams on the bottom per mole of sulfur. And that's going to give us here 9.34 divided by 3207, 0.2912 moles of sulfur here. Sulfur. So these two numbers here basically represent our starting amounts of each of these guys. That's how much we have of each of these guys to start with. Because it is a limiting reagent problem, and again, we know that from our 2 grams given to us, here we do need to figure out our limiting reagent problem, or which one is our limiting reagent. So what we're going to do is, like I said before, you could pick either reactant and do a calculation to figure out how much of the other one you need. So I'm going to do here to figure out my limiting reagent, if I want to use up all the iron, how much sulfur is needed. So what I'm going to do is start with my moles of iron that I started with, which is 0.1223 moles of iron. I'm going to go to the I'm going to go to the balanced equation and find my mole to mole relationship. This one's not too bad. It is a 1 mole of iron to 1 mole of sulfur relationship from the balanced equation. The coefficients is what we're using here. So using that here in our calculation, 1 mole of iron on the bottom to cancel, 1 mole sulfur up on top will tell me I need 0.1223 moles of sulfur is needed. First off, any question on that calculation there? Again, you could have done the opposite. You could have used your sulfur and figured out how many moles of iron you needed, whichever way you do it. Once I do that, I now need to compare it to how many moles of sulfur I started with. So in this case, I would need 0.122 moles of sulfur, and I am starting with 0.29 moles of sulfur. Do I have enough? I do have enough, right? And because I have enough, what that tells me is that the sulfur here is going to be my excess reagent because I have enough. And by default, the iron will be my limiting reagent just from that calculation. Any questions on that there? Now that I've identified my limiting reagent, I could pick back up with step number 3 and actually do the stoichiometry. It is important at this point that you do the stoichiometry with the starting amount of your limiting reagent. So you're not going to really use this calculation too much just to determine, how much, which ones are your limiting reagent. So coming back here to step number 3, using my limiting reagent starting amount of 0.1223 moles of iron, I now could do my mole to mole relationship between iron and my product, which also looks like it's a 1-to-1 relationship, so that's not too bad. Iron to my moles of FeS. So 1 mole of iron gives me 1 mole of FeS. That's going to give me 0.1223 moles of FeS. And if I want to know grams, that is going to need the molar mass now. So we're going to do step number 4, which is moles to grams in this case. So the molar mass is basically just these two guys added up. So if I add those guys together, I got 5585 plus 3207 can give me 87.92 grams per mole if I add my iron and my sulfur together. And I can now do really the last step in our calculation here. Here we do want grams up on top so that we do end up with grams. And again, this number came from the periodic table. The moles will cancel. And that's really our 4th step there. And that's going to get us here approximately 10.7, I'll call it 10.8 grams of FeS. And this again would be our theoretical yield. So hopefully you can see it's really the same 4 steps. You just got to kind of take that little time out in the middle to do that little calculation to figure out which one's the limiting. Once you do that, you could continue on. Again, in this case, you can see we figured out the excess, but by default, the opposite's happening to the other guy. So you don't actually have to go back and necessarily do that calculation. First off, any question on that there? Now, could I figure out how much of my excess reagents left over? I could. I know that my excess reagent is my sulfur, and I know that I would have needed, because I chose actually correctly in this case, I would have needed 0.1223 moles of it, and I started with 0.2912. So if I want to figure out my excess leftover, I could take the moles of my excess reagent I started with, and I could subtract it for how much I needed. And once again, if you didn't do that calculation, you would have to go back at this point to do it. But I did get lucky here. I did the right one, I guess. And we will subtract those two, 0.2912 minus 0.1223. That means that I would have 0.1689 moles of sulfur left over. And if I want to know how many grams that was, I could use the molar mass of sulfur, 3207 grams per mole. and times it by 3207. And I would have roughly 5.42 grams of sulfur once again left over. And we started with, I don't know where we started with there, but we started with 9.34 grams. So we basically used just under 4 grams of sulfur basically in this reaction, and we had just over 5 grams of it still left over. The amount of iron we would have left over should be 0 since it's the limiting reagent. Yeah. Any question on that there? All right. Roll that across. All right, so why don't you give this one a go? We want to know which one's a limiting reagent and how much of our product we produce. There's some molar masses. Okay, so let's take a look at it since we're getting to the end. Again, we're going to follow our stoichiometry here. We have a balanced equation. We are given the grams of each reactant, which means definitely we could get to moles. So even if the problem didn't tell you this is a limiting reagent problem, so we do need to include that sort of step. So second step, still the same. We're going to convert into moles. So 622.7 grams of NH3. They were, again, nice enough to give us the molar mass. If not, you would need to calculate it yourself there. And that's going to give us a starting amount here for our NH3 in moles of, we'll go with 36.565 moles of NH3. We'll do same calculation here for our CO2. Again, they also gave us the molar mass, which you would need to calculate, obviously, if they did not give it to you. And that will give us 1241 divided by 4401. That's going to give us 28.198 moles of CO2. These, again, are our starting amounts, basically, of each of these. Because it is a limiting reagent problem, we are going to do our calculation to determine which one's our limiting reagent. So again, you can pick either one. So I'll just pick the ammonia here, and I'm going to figure out if I want to use up all of the NH3, how much of that CO2 do I need? So I want to do the relationship between these two guys, and I can see it's a 2 mole of NH3 is 1 mole of CO2. So 1 mole of CO2 on top, 2 moles of NH3 on the bottom. The moles will cancel there of NH3. That will tell me that if I want to use up all of that, I would have to put in there 18.283 moles of CO2 is needed, basically. I'm going to compare that to the CO2 I'm starting with, and I can see I do have enough. So because I do have enough, that means that the CO2 here is our excess reagent. By default, our limiting reagent would actually be the NH3. Any question on how you determine that there? All right, now that we determined that, we're just going to pick up with our normal third and fourth step. We do want to make sure that we go back and use the starting amount of our limiting reagent. So going to kind of our third step now, we're going to take 36.565 moles of NH3. We now could do the NH3 to our product, which is 2 moles of NH3 gives us 1 mole of our NH3 2CO. So we're going to do that guy up on top. And we'll do our 2 moles of NH3 on the bottom. Those guys are going to cancel. And that will get us here 18.283 moles of our product here. And lastly here, we do want to figure out how many grams that is. So continuing on with our number there. And again, they were nice enough to give us the molar mass, or you would be going back to the periodic table at this point to do so. They gave it to us as 6006 grams per mole. Those are going to cancel, times it by 6006. Going to hit us about a 1,098 grams of our product here would be produced. And once again, that would be our theoretical yield. Any questions on those steps? So again, really the same basic steps, just got to insert that limiting reagent calculation. Any questions on that there? All right, we're laid up there for today.